All right, we'll begin. Okay, and looks like um, a lot of teams, maybe not every single team, but a lot of teams joined the Kaggle competition and posted kind of their your initial guesses, and everyone's kind of around the same place, around 0.018, 0.0179. A lot, one team has made a few more submissions and is scoring, ahead of everybody else. But overall, looking, just off to a off to a start here, and I anticipate that things will improve. Okay, so I encourage you to continue making submissions and improving your models and seeing how things go and improve. So good luck. All right. Okay. And then later this week, I will post another Kaggle competition, one for classification. Okay, so this is the regression competition where you are making numeric predictions, and then there will be another competition, same groups, but it will be a classification problem. Okay, and so that will get posted later this week. All right. Today we will take a look at our lecture, and so we will start to discuss classification models. Okay, and so a lot of today's content comes from Introduction to Statistical Learning, which gives an overview of different kinds of machine learning methods out there, and so we'll take a look at classification models, and then we'll also discuss a little bit how classification is done with tidy models. Okay, all right. So we'll go through this. So we use classification models when the goal is to try to predict a categorical variable. Okay, so when the response variable is a category, what we're trying to do is we're trying to predict what category or class an observation belongs to. And so, you either get the category classification correct or you get it wrong. Unlike with regression, you're trying to predict a number, and there are different degrees of how correct you are or how wrong you are. If you get it pretty close, you have small error, and if you guess far away, you have a large error. With classification, it's a little bit more all or nothing. You either classified it correctly and you guessed the correct category, or you got it wrong. Okay, and so we'll take a look at a few different methods. These are logistic regression. I imagine you have some familiarity with that, and as well as linear discriminant analysis. This is kind of an older method as far as classification. And then k-nearest neighbors is also a well-established and popular method, although they've fallen a little bit out of favor, with large data sets as well. Okay, we've talked about some tree-based methods already, and then there's other methods as well. So one of the kind of the example that we can look at in our from our textbook is this pretend or simulated data set where we are trying to classify basic like credit risk. So where this has simulated a bunch of people with credit cards and people who default on their payments. So that means they didn't make their monthly minimum payment. And basically, as a bank, if you are a bank and you are in the business of lending out money and charging interest, you can earn a lot of money, but if you lend money out to the wrong person, as in somebody who doesn't pay you back, then you lose money, right? And you can have penalties and whatnot. But basically, if the person kind of runs away, you're out of money. And so as a bank, you want to avoid lending money to people who are, I guess, risky, and but it's a little bit difficult to predict just because most people pay their debts, okay, and maybe only a small percentage of people default. And in our data set, they set that percentage of default to around 3%, and we're going to try to predict who defaults based on two factors: the person's annual income and their monthly credit card balance. Okay, and obviously there's lots of different factors, and one of the tricky things is you're going to have two people that have the same income and same monthly credit card balance, and one will default and one will not. Okay, and so rather than coming up with some kind of direct, when you have this much income and this much credit card balance, that means you're going to default. Generally, we try to make a prediction of probability. The probability somebody defaults is this number. The probability that somebody defaults is a different number. Okay. And another thing to try to improve our model's predictive ability. Okay, the overall rate of default is only around 3% in this data set that we have, and so if your model says no one defaults, if your model says no one defaults, no matter what, we're just going to predict not default, then you'd score 97% accuracy. Okay, so this is a useless model that doesn't adjust anything, but just because only 3% of the data set do miss their payments or do default, you'll still score 97% accuracy. So one of the different techniques we can do is we can downsample. Okay, and so this so just kind of in the plot to kind of give a sense, a little bit more of a balanced sense. Okay, we can do this. So we can downsample. Okay, those who didn't default. Otherwise, these dots over here would represent 3%, and then we would have like 97%, and this would just be like way more concentrated. So at least in this plot, we've downsampled, so it's only around, they're a little bit more even. Okay, and so just based on this plot where we are plotting the credit card balance and the income, okay, we can see in general, if you had to kind of draw a region, we would say, as your balance goes higher and higher to the right, the risk of defaulting gets higher. And, is there a relationship with income? It doesn't look like there's a very strong relationship, okay? But, yeah, maybe, as far as there would be a slight angled slope if you had to draw kind of a line to divide those who default versus those who do not. Default being the orange pluses, and then everybody who pays back being in blue. Okay, so we can just start off with some basic exploratory data analysis to kind of get a sense of the data. Okay, and so we'll begin by making a couple box plots, and so we'll show what is the distribution of balance, the credit card balance that they're carrying month to month, and we will separate it based on whether they default or not. Okay, and what we'll see is we see this kind of very pronounced relationship between those who default in orange and those who do not, and we can see kind of the median balance for those who do not default is around 800, whereas the median balance for those who do default is around 1,800. Okay, so we do see a very big difference, but there's also quite a bit of overlap as well. Okay, so those who don't default, goes anywhere from 0 to 2,000 with a few outliers over 2,200, 2,100, and then those who do default, their balance goes anywhere from 1,000 to, I don't know, 2,800 or something like that. Okay, so we do see big difference between those relationships. For those that do default, the balance tends to be much higher. Okay, this kind of difference doesn't exist in real life, but this is a simulated data set. Okay. Meanwhile, when we look at income, these two box plots are quite a bit similar. Okay, and we see a little bit more range on those who don't default, but that's probably because 97% of our data are in the no. Okay, and only 3% answered yes to, or not answered yes, but are classified as those that do default. But we do see as far as the location of Q1 and Q3 and the median, they're all kind of very similar to each other. Okay, so we don't see a very big difference between the distribution of those that default and those that do not. Okay, so as we do classification models, somewhere along the way you might just wonder, well, can I just treat this like linear regression? And this can happen a lot of times by mistake if your categorical variable is, say, numeric, okay? Or not numeric, but if your categorical variable is classified using integers. So for example, you could have medical condition, and you might categorize, rather than using words, you might have, stroke is category 1, drug overdose is category 2, epileptic seizure is category 3, or something like that. Okay, and if you're not careful and you just have and you just kind of throw it into R and you say run a model, okay, R will see these things as integers and treat them as numbers. And that's going to lead to problems, because when things are numbered, there's an inherent order. 3 is bigger than 2, 2 is bigger than 1, okay? And so, it's kind of silly, but, if this is the case, 1, 2, 3, then that means drug overdose is somewhere in between stroke and epileptic seizure, which, of course, doesn't make sense, okay? But if you treat these as numeric, like in numbers, the number 50 is halfway between 0 and 100, okay? And the number 2 is halfway in between 1 and 3. And so if you have things like this, it's going to say this category is halfway between 1 and 3, which is not the same, okay? And then the difference between 1 and 2 is the same as the difference between 2 and 3. Again, doesn't make sense for something like this where it's categorical, okay? So that's why, when we encode things into our system for prediction, okay, because our prediction does ultimately need numbers at the end, right? We're doing a bunch of kind of numeric computations. We turn them into dummy variables. We make a column for stroke, and it's either a yes or a no, a 1 or a 0. We make a column for drug overdose, and it's either a yes or a no, a 1 or a 0. Okay. Okay. So for these unordered outcomes, okay, it doesn't make sense to try to make categories. So yeah, we don't do this. Okay. Right. So this is also another reasonable coding, okay? Here, if I say number 1 is epileptic seizure, 2 is stroke, and 3 is drug overdose, okay? We've rearranged these things, okay? And now we're saying stroke is somewhere in between seizure and overdose. Again, doesn't make sense, okay? So there are a couple exceptions to this rule, and numeric coding could work if you have ordered outcomes, like if there's a natural ordering. So if you want to go from like clothing size to a number, okay, and you go small, medium, large, extra large, that's okay, all right? And in fact, so in America, when you go to the store, you can buy small, medium, large, extra large. But there's also dress sizes that go from like 0, 1, 2, to whatever. I don't know how dress sizes work, right? And then in other countries, there's numeric things, and when you buy shoes, there's like a number inside there's a tag that converts the American shoe size to like the European to like other countries' shoe sizes, and it's, I think, shoe sizes technically aren't like strictly numeric, but I think you can treat them like numeric, okay? Because as far as shoe size goes, it's not that shoe size 2, or like a shoe size of 6 is not twice as big as a shoe size of 3, right? Okay, it's only going to be like, I don't know, a centimeter or 2, a few centimeters difference, but it's not like, and then you want to go to shoe size 0, and that means your shoe disappears, okay? Versus something like weight, something that's 6 kilograms is twice the weight of something 3 kilograms. But, going from a natural ordering, I think that's okay. Even things like star ratings on like product reviews, we end up kind of treating these as numeric, and we just kind of take the average of them, right? So when they ask you to leave a review, you can give it 5 stars, 4 stars, or 3 stars, and then we kind of just average these things, and that's okay. Like if it makes sense that you can take an average, then it's numeric. It's close enough to being numeric, okay? But unfortunately, I don't know, our review system is all messed up now, and it, like, if you get an Uber or something, or you order DoorDash or something, it feels like if you don't do anything, if you don't give 5 stars, you're basically saying the person did a terrible job, which unfortunately I don't think is how it's supposed to be. But because it's like average is now 5 stars, and then you have no way to say like what's above average, but but anyway, okay. And then you could also do zeros and ones, and that's fine. Okay. So, when we do logistic regression, we're basically going to try to predict the probability of a yes response, okay? So as far as what's the probability that somebody defaults, okay? That default is equal to yes, given, say, the balance, okay? And so this is going to be basically the probability that we want to calculate, and effectively, because the value that we're going to input is going to be balance, okay? We can just call this P of balance, the probability based on the balance. This is going to be a function, and it's going to output a value between 0 and 1, okay? And we might say we could predict someone's going to default if balance is greater than 0.5 or something, and then you could have different thresholds. And as far as like, if you are a bank, you might not want to just try to predict if someone's going to default or not, but you might just say this person is a higher risk if their probability of defaulting is over, say, 10%, okay, or something like that. So here, this is a plot that shows that we need tools more refined than linear regression, okay? So with linear regression, again, our responses are either the person did not default or the person did default, okay? And so that we only see values at 0 and values at 1, okay? And this, anytime you see horizontal lines in your plots, it means basically there's some kind of, it's behaving almost like a categorical or discrete variable, okay? Even if it's numeric, continuous, if your measuring tool can only do like whole numbers, you're going to end up with horizontal bands. And so, with a straight line, this doesn't work because obviously we can't go negative, and then even at the highest end our probability of default is maybe 30% or something, and eventually it'll, if you extend this blue line, eventually it'll cross 1, but yeah, linear regression is not going to be good enough. And so, you know, we have this curve. This is the logistic curve, and the logistic curve has a range going from 0 to 1, and basically values over here just will asymptotically approach 0, and then as it goes over here, they asymptotically approach 1, and so this is going to be far more useful. And so this is where logistic regression gets its name, because this function that converts values to this range of 0 and 1 is known as our logistic curve. Okay, so the logistic curve is basically e to something divided by 1 plus e to that thing. Okay, and so we're just going to take the linear regression line, which is an intercept plus slope times x, and plug that into e to the x of that thing. Okay, we're going to just have e raised to that whole thing. And so when x is, you know, if your slope is positive, and so when this quantity ends up being very positive, okay, like 1,000, okay, basically you have something approaching infinity divided by 1 plus infinity, and so this is going to approach 1, okay? And on the other hand, when this thing is very negative, okay, e to something very negative comes close to 0, so you're going to have something very close to 0 divided by 1 plus effectively 0, and so this will approach 0, okay? And then if you plug in, if this whole quantity is equal to 0, then you have e to the 0, you have 1 in the numerator, and then 1 plus 1 or 2 in the denominator. And so that will be equal to, where beta 0 plus beta 1 x is equal to 0, this thing is going to equal 1/2. And then this transformation going from the line into the logistic curve can be undone, known as the by the logit function or the log odds function. Okay, and this is the inverse of the logistic function. And so if you take this this p of x function and you plug it into the logit function, so you do p of x divided by 1 minus p of x, and you take the log of that, that will undo it, and you will get back your linear equation of intercept plus slope times x. And so the interpretation of this is that if x increases by 1, okay, if x increases by 1, then this quantity of the log odds, okay, if the log odds will increase by the value of the slope, okay. So, you know, in normal linear model, we say if x increases by 1, then our prediction increases by beta 1, okay. And with the logistic, we say if x increases by 1, then this quantity, which is known as the log odds increase by beta 1, okay. So the log odds is kind of it's a weird thing, okay? The log odds is the log of the odds function, okay? Probabilities are really easy to understand, okay? Odds can be understood with some challenge, and log odds really only make sense kind of in this imaginary hypothetical scenarios. Okay, and we don't really work with log odds very well. But I do want to explain how changes in percentage points and probabilities correspond to changes in odds. Okay, so if we say something improves by 5 percentage points, that is generally pretty easy to understand, right? So we could say, right now your probability of success is 20%, and if you take this action, your probability of success increases to 25%, okay? And that makes simple sense, okay? if we're talking about odds, however, a 20% probability of success, okay, is an odds of 1 to 4, right? You do 0.2, the probability of success, divided by the probability of failure, okay? So probability of failure is 80%, 1 minus 0.2. So 0.2 divided by 0.8 is 0.25, or basically 1 success relative to 4 failures, okay? So this is, your odds are 1 to 4, okay? Meanwhile, a 25% probability of success, okay, corresponds to an odds of 1 to 3. So basically, 1 chance of success for every 3 chances of failure. So 25% success, 75% failure, so 1 to 3 odds. And so adding 5 percentage points to the probability of success goes from 20% to 25%, but that changes the odds from 1 in 4 to 1 in 3. So you basically go from 0.25 to 0.333, or your odds change by 0.0833, okay? It's even more strange at different locations, okay? So your probabilities can go from 0 to 1, whereas the odds don't really have an upper or lower limit, okay? So let's say your current probability of success is 90%, okay? And if we add 5 percentage points to that, you go from 90% probability to 95% probability, okay? This corresponds to a very big change in the odds, though, okay? The odds go from a 90% probability corresponds to 9 to 1 odds, or basically an odds ratio of 9. So 90% probability divided by 10% failure, so that's 9 to 1 odds, okay? Whereas if you add 5 percentage points to your probability of success, now your probability of success is 95%, and now your odds are 19 to 1, right? So if you do 95% probability of success divided by 5% probability of failure, 95 divided by 5 becomes 19 to 1, okay? So adding 5 percentage points has increased our odds by a quantity of 10, okay? So we went from 9 to 1 odds to 19 to 1, okay? Versus over here, adding 5 percentage points, we went from 20% to 25%, but our odds go from 1 to 4 to 1 to 3, and here we're going from and then if I added another 5% here, 95% probability, then it goes up to 100% probability of success, and then your odds are infinity, okay? Your odds are basically infinity to 1, which is just we don't have a way to go, okay? Odds are useful when you have like really extreme probabilities, okay? So the difference, it doesn't feel like there's a very big difference between like 99% versus 99.9% versus 99.999%, okay? Like those all sound kind of similar. Like if I So 99% versus 99.9%, 99.999%, okay? How do I zoom here? Okay. So 99%, this corresponds to basically 100 to 1, right? For odds. This is 1,000 to 1. And then this would be, what is it? 100,000 to 1, okay? So I'd say quite a big difference between each of these things, okay? 100 to 1, 1,000 to 1 versus 100,000 to 1. Okay, and things like airline safety. Okay, airline safety is on the order of, it might even be higher than this. Okay, like it might even be like you add a couple more nines here. Right? I don't know what it is. It might be like 10 million to 1 or a million to 1 type of thing, or like miles flown and things like that in terms of risk of failure. Okay, because if you only had, if airline flights were like 99% reliable, okay, meaning 1% of flights had an accident or something, okay, we're talking about thousands of disasters, like a week, okay, and that, so we use odds to kind of rate these extreme things because I think it better captures the difference, okay, because I don't know, 99.9 versus 99.99 doesn't feel like a huge difference, but these are factors of 100, okay, difference as far as the odds go. Okay, so this is 100,000 versus 10 million. 100,000, and this is 10 million. Yeah, so quite a big difference. All right, so how do we estimate these things? These are done via maximum likelihood estimation. Okay, we're going to try to find the intercept value and the slope value that's going to maximize the likelihood of our data, and our computers can do that for us quite efficiently. It's going to try to maximize looking at how many responses are yes versus no. So it will find that, okay? And so it's going to try to find the intercept and slope that will maximize the probability for the observations that have defaulted, and it's going to maximize 1 minus that probability for all the observations that didn't default, okay? And so, just using kind of the base model in R is just GLM, okay? And this will allow us to fit a logistic regression, okay? And so we can just say, hey, predict the probability of defaulting based on the variable balance, okay? And then the family that we run is called binomial, and this is because our errors will be either basically zeros or ones rather than normally distributed. And so when you do that, the output of this gives us a quantity for the intercept and the balance. So this is going to basically our slope on the log odds, and this is the intercept for the log odds. And we see that both of these things are very significant. Okay, we can see we're almost 30 standard deviations away or 25 standard deviations away, and so very significant. Okay, if we wanted to do the same kind of thing and fit a logistic regression model with tidy models, we can do the same thing. So I'm just going to call it library tidy models. And here, among the different models that are available, you can just set up logistic regression. So, instead of linear underscore regression, we call logistic underscore regression. We can set our engine. There is a variety of engines available to us. So as far as the different models go, we can look at the reference for logistic regression, and there's a whole bunch of different engines. Okay, so the default is GLM. Okay, and then there's others that you might need to install some extension packages to take advantage. Okay. The default usage is mode is classification and engine is GLM. So if I don't specify anything, it will default to using GLM. And then there's other arguments like the penalty and kind of as far as having, do you want to use, you can apply regularization like lasso and ridge regression, okay, by adding in a penalty or things there. Okay, so anyway, we'll take our model and we'll fit it to our data. We just say fit default, predict default based on balance, data equals default. Here I specify the formula here. I could have set up a workflow where my recipe is basically just the formula of default versus based on balance, but here I'm just taking the model and directly fitting it to our data. Okay, and so the results here, we get the same coefficients as far as our intercept and slope coefficient. It's just not formatted in scientific notation. Back here it was 5.499 times 10 to the minus 3 and negative 1.06 times 10 to the 1. So negative 1.06 is basically 10.6, and then 0.00, 5.499 times 10 to the minus 3 is this. Okay, so these are the same coefficients as we would expect. And then, if we're using tidy models, then basically our summary statistics for each of the coefficients can be organized into a table using the tidy function. So we could take the resulting fitted model, throw that into tidy, and it gathers up all of that information into a table. Okay, and this has all of the same information again as the summary output table. So we can see on this thing we have the standard error of 3.6 times 10 to the minus 1 and 2.2 times 10 to the minus 4 with z-scores of negative 29.49 and 24.95. And we can see those are right here. Negative 29.49 is rounded off to negative 29.5, and 24.9, whatever is that, and 3.6 times 10 to the minus 1 and 2.2 times 10 to the minus 4 is what we have here. Okay, and we have more precision in our p-values. Rather than just saying it's less than 10 to the minus 16, we actually see it's 10 to the minus 191, which is kind of astounding, but indeed we have these p-values. Okay, so as far as the tidy models. So as far as what our coefficient on the balance is, okay, our coefficient is 0.0055, and again, this is how much our log odds change when our x variable balance increases by 1, okay? So we're saying if someone's balance goes up by 1, their log odds go up by 0.0055, okay? Again, the exact interpretation of that number is kind of hard because it's not even changes in odds, it's changes in the log odds, which is, weird. But it is positive. So what that means is that as the balance goes up, then so does the probability of default. Okay, so the probability of defaulting also increases as the balance goes up. And so we can see that the summary table also includes the z-statistics and p-values, and they indicate that it is significantly different from 0 because our p-value is very small. Okay, if the p-value were not significant, so if we didn't have such a tiny p-value, but we had something like 0.2 or whatever, that would indicate that the results in our data could have been the result of random chance, and that this variable, whatever it might be, is not really associated with a change in the probability of defaulting. Okay, as far as using tidy models to make predictions, we can do that. And so once we have our fitted model, we can make a prediction, and then we can put in a value here. Okay, so we can say, okay, if the balance is 1200, what do you predict? Do you predict the person is going to default or not? Okay, and so our predicted class is going to be no. Okay, so the output of predict on a logistic regression, the default output is going to be basically a class, and so we can predict yes or no. It's probably more useful to us if we have a probability prediction. And so if I say, our balance is 1200 and what I want is a probability prediction, okay? Type is equal to probability. We can say probability of no is going to be 0.983 and probability of yes is 0.017, okay? And then we can change the balance, okay, to something higher, and we can see how this affects our probability. And so if the balance is 2000, probability of default here is, around, probability of default is 0.586. Prediction for no, probability there is going to be 0.414. And then if our balance is up to 2500, then our probability for yes is up to 0.957, and the probability for no is down to 0.0433. So, with logistic regression, you can just predict the class, and I think the threshold is at 50%, okay? But then you can also you can predict with the probabilities, and you'll get probability for each of these classes here, okay? All right, how do we measure the performance to evaluate, is our model doing a good job, okay? So one of the most kind of basic things we can do is create what we call a confusion matrix. Okay, and a confusion matrix, all it does is it says along one axis you have the true values, and on the other exact axis you have your predicted values. So as for our credit default, our categorical variable is either going to be yes or no. Yes, they defaulted, or no, they didn't. Okay, and so our confusion matrix is basically saying if the true answer was no, we predicted no 9,625 times. When the true answer was no, they didn't default, we predicted, we were wrong and predicted they would default 42 times. Okay, when they did default, if the truth was that they did default, we predicted no, they wouldn't default 233 times, and we got it right 100 times, okay? So basically your off diagonals are where you made a misclassification, okay? And this is done by kind of taking your predictions, okay? So we're going to take our default data set, we're going to take that column, whether they defaulted or not, we're going to call that the truth, okay? And then as far as the new columns, we're going to have a column called predictions, okay? Or I guess our dot predicted class. So the output of predict on the logistic fit, where our new data is basically everything but that default column. Okay, oops. I'm just taking this column of predicted class, yeses and nos, okay? And we're binding it together here. All right, and then we have tidy models create the confusion matrix based on this table. So you just have this table of default and predictions is just one row for every observation. What was the actual value? Okay, whether they defaulted or not, that's going to be the truth. And then what did you predict? We put that under estimate, okay, as the dot predicted class. And then it creates the confusion matrix, okay? So as far as our straight accuracy goes, okay, I think there's a total of 1,000 observations, or 10,000 observations, but let me just add this up. 9625 plus 233 plus 42 plus 100, right? So yeah, total of 10,000. And so our accuracy is basically what we have down the diagonal. So we have a total of 9625 plus 100. So we have divided by 10,000. So we're at 97.25% accurate. Okay, so that's our straight accuracy. Okay, so if we have this table here, we can just ask, what is the accuracy? And the accuracy is basically if your predicted class and the truth are the same, that's correct. And if they're different, it's wrong. And so we could see, yeah, we got it correct. You just look at the diagonal. 9,625 plus 100 is 9,725. And so your accuracy there is 97.2%. Okay. We have a few other accuracy measures, okay? And so we have what's called the MCC, the Matthews Correlation Coefficient, or this is the phi coefficient, okay? And if you get a coefficient of +1, that's a perfect, that means you predicted everything perfectly. 0 is the same as random prediction, and -1 would be kind of the opposite. You managed to predict everything just the opposite. Okay, so like a -1 is just as impressive as a +1. It's just if you get -1, you just flip all of your things around. Okay, so this is you can look at the Wikipedia page on how the phi coefficient or the Matthews correlation coefficient, okay, regarding how it's calculated, okay? And so you basically take the product of how many you got correct minus the product of how many you got wrong. So the diagonal elements are multiplied together. That's like your correct ratio. And then on the top, and then the off diagonal is basically the ones you got wrong. And then you divide by the total number of basically your row totals and column totals for all of these things. Okay. So we're getting a phi correlation coefficient of 0.449. Again, all of these things are, your measures of performance are really only good if you have another model to compare it to. Okay. You have also the F-score. Okay. And so F-score is known as the harmonic mean of precision and recall. These are kind of terms that are a little bit strange, but basically, you have what you have. How are they correctly classified? Okay, so all of your the relevant elements here. Okay, these would be everybody who defaulted. So I don't know if I can label this. So according to this picture. Okay, so your relevant elements, this is everyone who defaults, default yes, okay, and then this would be like a no default. And then these are your selected elements, okay, so these would be, this is properly flagged, properly labeled as default. Okay, and then these would be kind of like your false positives. So these would be like, I guess, safe borrowers. So these would be like people who are risky that were rejected from the loan, and these would be like people who should have gotten the loan but were rejected, right? Rejected, but did not default. These are people who basically did not default and were approved. Okay, and then over here, these are your false negatives. These are people who do default but were approved, okay? Approved for a loan, but defaulted. Just write big T, okay? So the false negatives, so your precision is basically what proportion properly labeled as defaulting divided by everybody who got flagged as potentially defaulting. Okay, so you want this to be high. Okay, you want your precision is basically how correct, like the number of basically defaulters divided by basically number of, I guess, rejected applicants. So if somebody applies for a loan, okay, it'll be like the number of rejected applicants divided by, or the number of people who would default divided by the number of rejected applicants. So you want this to be like 99%. Okay, if this is 99%, that means of those people who you rejected for applications, like 99% of them were going to default, and only 1% was a false positive. Okay, and then the recall is basically of those is the properly labeled, like people who would default, divided by the true population of everybody who actually does default, right? So like how many were like in the entire population, okay? So there's like number of actual defaulters, number of actual people who default, divide, and then that's in the denominator, and the numerator is like people who are kind of number flagged by the system, flagged as rejections. Okay, and if that's 99%, that means you're properly flagging 99% of the people who are going to get rejected. Okay, so that's your precision and recall. And so if you do that, okay, then our F measure, okay, so yes, the default is the event of interest. Our F measure is 42%. Okay, if you flip this around and you say no is the event of interest, so like you're like flipping it around and you want to say like not the number of defaults, like, but it's like the number who properly pay back their loans divided by everybody who's approved, and then would be your precision, and then your recall would be the number who actually I'm trying to think. It's I gotta the recall there would be the number who you approve for loans divided by the population of everybody who should be approved for loans. Okay, and so that you end up getting, I guess, 0.986. Okay, so the F measure is going to be higher in general for the categories that are easier to predict. Okay, so in our case, because like 97% of people don't default, okay, it's like much easier to predict that. Okay, and because only 3% do default, it's a lot harder to predict, and so our F score here is much much lower, okay? But this is probably a better reflection of like our model's accuracy, okay? And so the F measure, I'd say, is recommended, especially for imbalanced categories. And draw this diagram, label everything, and ask yourself, like, what does it mean to properly predict these things? Okay, so here's the diagram from Wikipedia as well. Okay, and so here is, so that's that. Okay. Oh, we can also make a logistic regression model using a categorical predictor. Okay, so one of the predictor variables in our data set for whether a person defaults on their loan or not is the person a student. Okay, and according to our model, if the person is a student, they are at a higher risk of defaulting on their loan, okay, or on their credit cards, and we have a positive coefficient here. Not dramatically higher. Our z-score is 3.5, so it is still positive, but it is positive there. Okay, so we can do that with tidy models. We do the same kind of thing. We just say, hey, we want to make a logistic regression model, and then we fit it, and then again, here's our estimate, 0.405 is our coefficient, and our p-value is 0.000431. Okay, over here we get p-value basically 0 with a z-score of -49. All right. So with a categorical predictor, we're fitting a logistic regression. Okay, is the person a student or not? And if they are a student, they are at a increased risk. Okay, but it's not dramatic. Like if you look at the predictions, okay, if we predict what's the probability somebody defaults if they are a student, okay, the probability that they default is 0.043, around 4%. Okay, and if they're not a student, it's around 3%, 0.029. Okay, so it does, yes, there is a difference. If we find out somebody is a student, their risk of defaulting does go up a little bit, but if they're not a student, it's a little bit lower. Okay, but again, not dramatic there. Okay, now and so that's using the categorical predictor. Multiple logistic regression is kind of like the way we did linear regression. You just kind of add additional terms, and now you have a linear combination of predictors, and your logit function is going to be determined by this linear combination. Okay, so basically, as any of these predictors go up or down, your logit, your log odds also predicted go up or down. And so, interestingly, okay, if we do this and we're going to say, all right, let's make a model where we're going to try to predict whether somebody defaults based on their credit card balance, their income level, and whether they are a student or not, okay? And so when we include all three terms, what we find is there's a positive correlation for balance, okay? There's a positive correlation for income, but it is not significant, okay? Which reflects what we kind of saw in our early diagram. So what is this? I'm on slide 35. So in our early diagram here, okay, where we're looking at balance and income, we see definitely there's kind of a difference between balance and income. Higher balance, definitely more orange dots. But if I said, hey, is there a line where you could draw for income, where you can say, like, above this line, people seem more likely to default, and below this line, they're less likely to default? It's hard to draw like a horizontal line here, okay? So it doesn't look like there's a huge relationship between income and balance. And so that's That's reflected in our coefficients in that we don't have anything significant here. All right, this is interesting though. Student yes, we now have a negative coefficient, okay? And this negative coefficient indicates to us that being a student decreases the risk of default, okay? Which seems to be in conflict with what we found back here, okay? We have a positive coefficient for student yes, and now I have a negative coefficient for student yes, okay? So what's going on there, okay? Oh, here's the same thing. I do it with tidy models, and I have, I gather everything up in tidy. So we have positive for balance, negative for student, okay? You know, our p-values are significant for balance and student, but not for income. Okay, so what's going on here? So for the credit default data, we see the coefficient for balance is still significant and positive, indicating that a larger balance is associated with a higher probability of default. Okay, and coefficient for income is not significant. Okay, but then we see that the coefficient for student yes is negative and significant. Okay, and so this does at first appear to be in conflict with the logistic regression when we did predict just on student alone. Okay, all right, and so what this means is that if we keep the variables balance and income fixed, all right, so for a given balance and income, then a student is less likely to default than a non-student with the same balance and income, right? And so if we look at our default rate, okay, we see for the same kind of, if you plot credit card balance, but you distinguish between students and non-students, okay, we see the orange line for students is lower than the blue line, which is non-students. So as far as credit card balance goes up, so if, you know, at 1,500, okay, the orange line is below the blue line. Okay, at 2,000, the orange line is below the blue line. Okay, at 1,800, it's below the blue line, right? So kind of along the curve, the probability that a student defaults is lower than the probability that a non-student defaults. Okay. However, the overall rate of defaulting for students is higher than non-students. So what's going on? Okay, if we look at the balance variable in our data set, okay, it appears that students overall carry a higher credit card balance than non-students. Okay, so this is the difference, is that there is kind of a difference in population. There's a relationship between balance and student status, and so overall students tend to carry more credit card balance. Credit card balance is highly associated with default rate, okay? But given this two people with the same credit card balance, somebody with, if two people have the same credit card balance, the student is less likely to default than the non-student, is what we have here. All right, so that is, that's what we cover on logistic regression. Okay, I'm gonna keep going here, and we'll introduce another classification method, and this is linear discriminant analysis, and this is related to the Bayes classifier, or is it, you know, and actually in 102B later today, I'll cover the Bayes classifier here. But basically, we want to make a distribution of our x variable for each of the different classes in y. So we can say if, so, you know, we might have some kind of numeric variable x, like say height, okay? And we might have different classes, maybe classes based on gender or something like that, right? And so we can say, okay, if somebody is a man, what is the distribution of height, okay? If somebody is a woman, what is the distribution of their height, okay? And we can say, based on these different classes that might exist, we can make a distribution for each of these x variables. And so that's going to be, we're going to estimate what the probability of X is based on the class, okay? And then once we have that information, we can use Bayes' theorem to try to get what is the probability that somebody belongs to a class given their X variable, okay? So basically, it's kind of, again, kind of just this very simplified height example. We can say in general, right, if somebody, for men, the distribution of heights maybe is centered up here, 5'9", 5'10", and in general, the distribution of heights for women is shorter, okay, maybe centered around 5'4" or whatever, right? So we'll basically, what is the distribution of X based on our class? We're going to just basically come away and say something like, in general, men are taller than women. Okay, of course, there's a distribution around it. And therefore, if you have a new observation and the person is very tall, okay, if X is high, then we're going to say the probability is going to be higher that the person is a man versus a woman or something like that, okay? So tall people, higher probability of men, shorter people, higher probability of women, based on this kind of very simplified example. And so, this is just an application of Bayes' theorem, which says, if you want the probability of A given B, you can calculate it this way. Probability of B given A times the probability of A divided by the probability of B. Okay, and so, what we're going to use this quantity. This is what we call the likelihood. This is the density function of X for a particular class. We're going to have different density functions for each class. But then we also have what is the probability of each of these classes prior to kind of looking at the X variables, okay? So this is the prior probability that an observation comes from a particular class. So this is helpful if you have like class imbalance. So, if, in the general population, you might be around 50% men, around 50% women in the general population. Okay, maybe a little bit different, including some, non-binary individuals. But then, depending on where you're drawing random individuals, okay? So, at UCLA, certain majors, there's a gender disparity, okay? So some majors, there's more men. Other majors, there's more women. And so let's say, if you just randomly pick somebody from, one of these majors where there's an imbalance, the prior probability before you look at any of the information, you might say, okay, before I even look at any of the data, I'm going to say there's a higher probability that the person I've selected is a woman, okay? And then you look at the information and you say, oh, this person is really tall. So could be a tall woman, or it could be one of the rare men who is tall, okay? Or something like that, right? Okay, marginal probability on the denominator. This is the probability of just getting some particular X value across all possible classes. And basically, we just calculate the numerator for each of the different classes. So let me, all of this stuff. This is a lot of kind of theoretical equations, but let's just kind of try out some kind of example, okay? So here is, we're going to do linear discriminant analysis with just basically one predictor here. And we're going to just assume our values come from normal distribution. And we're going to assume both classes have the same variance, okay? And so the density function is this, and I can just use d norm in R to get this, okay? So basically, when we're trying to calculate the linear discriminant analysis here, the Bayes classifier, I'm going to just kind of take my prior probability for each class, multiply it by, I'm going to say, what is the probability of getting this particular X value, okay? If we assume one is centered at the mean mu, and use has a standard deviation of sigma, okay? And then we're going to kind of calculate it for a particular class K, and then we're going to calculate it for all of the different possible classes, okay? So this L here says try it out for class 1, class 2, class 3, and so on and so forth, okay? You can do some kind of algebra and manipulate some things around, and you can calculate this, all right? And this delta K is basically, which you're going to get different values of delta K for each of your different classes. And you pick the one that's the largest. So basically, here I've got two distributions, a green distribution and a pink distribution. The pink distribution has a mean of 1.25, and the green distribution has a mean of negative 1.25, right? And so if you observe an observation, say, at 2, okay? Or let's say positive 1, okay? Let's say you observe an observation at positive 1, okay? At positive 1, there's a much higher probability that it comes from, say, the pink distribution than the green distribution, okay? And if both of these have equal probability prior to it, then we'd probably classify it as pink, okay? And similarly, if you observe something at negative 1, okay? Now, there's a possibility that it's from the pink distribution with just kind of like a very low value. It's possible, but overall, we would classify it as green, okay? And so in this case, with only kind of two classes, we can calculate kind of our threshold. And basically, if x is greater than 0, we would classify as pink. And if x is less than 0, we would classify as green. But that would be like the hard line, whereas, there's kind of a probability thing. So when x is greater than 0, the probability that it's pink is over 0.5. And when it's less than 0, there's still a probability that it's pink, but, in comparison to the green, it just gets lower and lower, okay? Right at 0 is where both of them are equal. Probability is 50%. But this is just based on our data. This is kind of what we have. And so, yeah, you could have an observation that's green, that's at like 1.5. But again, observations at 1.5 more likely to come from the pink distribution. So this is the case there, okay? Figuring out your density function is non-trivial. Things are a lot easier if you just assume things are normal, okay? And so a lot of times we do kind of assume normality. The normal distribution has a lot of nice properties. If that is a bad assumption, then your linear discriminant analysis classifier is going to have some problems. But a lot of times, even if it is a bad assumption, assuming things are kind of normal often works out. I would say it only blows up if your data is like extremely, extremely skewed. And in that case, you might want to apply a transformation. But a lot of things are kind of unimodal, kind of symmetric. And if it's kind of unimodal, kind of symmetric, then the normal distribution is going to do a good job of approximating it, even if it's not perfectly aligned, okay? And when you do assume the normal distribution, then you really only have to worry about estimating the mean. You don't have to worry about all of your variances and whatnot, okay? And estimating the mean is super easy because all you have to do is you just take the sample mean, okay? Sample mean for each class, you just say, all right, for this particular class, let's take the mean. And for this particular class, let's take the mean. So you just take your training data and you say, all right, what are the different classes I have? And you calculate sample means for each of your different classes here. Okay. you basically calculate the variance across all of the different classes. Estimated variance for all of the classes is the average square distance from the class mean averaged across all of the possible classes, okay? And then your prior probabilities is you just say, okay, in my training data, I have this many observations from this class. You just basically take your sample proportions. Sample proportions will act as your prior probabilities, and that works out similarly, okay? Linear discriminant analysis can be generalized to multi-dimensional data, so you don't have to just look at one variable, but you can now start looking at multiple variables. So basically you can take into account like height and weight, or these different variables that are out there, right? Flipper length and flipper beak length and whatever for like penguins data and stuff like that, okay? And for higher dimensional data, we're going to assume our values come from a multivariate normal or multivariate Gaussian distribution. And again, we're going to assume kind of our variances for all of the different classes are the same. Oops, sorry. Okay, so we can do linear discriminant analysis using this function LDA, and this is in library mass, and then I think I have it in tidy models as well. Discriminant linear here. Okay, say linear in tidy models, you can do linear discriminant analysis using mass as well, but here it is. Okay, and then so here we're going to say predict whether someone defaults based on balance and whether the person is a student or not. Okay, and then we can ask, make predictions, and then make a confusion matrix. And so this is what it gets, okay? And so it is misclassified. Our error rate is around 2.75%, okay? So, 23 plus 252 gives me 2.75%, which feels good, but again, our default rate in total is only 3.33%. So our classifier does only slightly better than our default, okay? Here I'm going to do the same thing using tidy models. We're going to create a linear discriminant analysis, set engine mass, predict default based on balance and student. This is our resulting fit, okay? And then we can make predictions, and here's our confusion matrix. So these results match as well. And we can ask, what is our F measure for discriminant analysis? So with tidy models, you can create, gather your metrics, okay? So we can say, hey, I want to know accuracy. I want to know our phi or our Matthews correlation coefficient, and I want to know our F measure, our F score, okay? And so we do this, and it gives us all of our different scores. Our accuracy is 97.2%. Our F measure is only 0.371, so not super great. Okay, our sensitivity is the same thing as precision, I believe. Let me just kind of. Oh no, it's not. Sensitivity. So precision is this. You have precision, recall. You also have sensitivity and specificity. Okay, so sensitivity is how many relevant items are selected. That is, how many sick people are correctly identified as having the condition. So of those that actually default, how many are correctly identified as going to default? That's your sensitivity. And then the specificity is how many negative selected elements are truly negative. So how how many healthy people are identified as not having the condition. So how many people who won't default are correctly identified as not defaulting is your specificity. Okay, so we can also get that. So your sensitivity is going to be 81 divided by the sum of those that will actually default. So of those that actually will default, we have 333, 252 plus 81, right? 252 plus 81. We have a total of 333 people who actually will default, and we correctly identified 81 of them. So 81 divided by 333. So our sensitivity is only 24%, so not super great, okay? And you can get that by asking for sensitivity. And then the specificity is basically this column of no, right? We have 9644 plus 23, 9,667, and we correctly identified 9,644. So our specificity 9644 divided by 9667, 99.7% is our specificity, or 0.99, I guess rounded, 0.998. Okay, so that's that. Oh, and here are the here's the math there. Okay, and so we might want to change some of these numbers regarding like whether somebody will default or not. Okay, and so we can adjust our threshold. Okay, so we can say lending to someone who defaults could leave the bank with a loss of a potentially large loan. Meanwhile, turning away good customers, okay, will lead to a loss of collected interest, right? And so if you're a bank, you have to weigh these two kinds of mistakes, right? One is you lend money to somebody who doesn't pay you back, and then the other is you reject somebody who was going to pay you back. And you might say, okay, well, between these two kinds of mistakes, it's worse to lend money to somebody who's not going to pay me back, or something like that, right? And so rather than just using a threshold of 50%, okay, we can just say, hey, you know what, we're going to turn away anybody if their probability of default is 0.2. Okay, so we can lower the threshold at which we reject somebody. Okay, so we can do this, and we can say, all right, using our predictions, okay, we'll look at prediction yes, prediction no, and then we're going to make predictions yes or no based on this probability, all right? And so we're going to change our threshold to, say, 20% rather than 50%, okay? And so if we do that, now we're rejecting a lot more people, right? We're rejecting a lot more people because if their risk of default is higher than 20%, now we're going to reject them. And so now our sensitivity goes up to 58%. Okay, our sensitivity goes up to 58%, and our specificity goes down to, say, 97%. Okay, so our values change. So of the 333 people that do default, okay, now we're correctly identifying 195 out of them. Okay, we're still missing 138. Okay, but now we're having a lot more false positives. Okay, so our false positive rate is much higher, and our specificity is going down. Okay, so this is kind of, I don't know, if you've ever applied for a credit card and the bank rejects you, okay, because they think you're either a risk or a fraud, this is a fraudulent application, things like that. Basically, they've increased their sensitivity, which means there's going to be more false positives, okay? You can further adjust your thresholds, okay? So now we can say if anybody has a risk of over 10%, we're going to reject them. And so in that case, our sensitivity goes up to 75%, okay? But our specificity goes down to 94%. So now we're having a lot more false positives, okay? We're rejecting a lot of like customers who would have been fine, okay? And so this plot shows kind of how you're at different thresholds, okay? At different thresholds, we have different kind of error rates. So as we increase the threshold at which we reject someone, okay, the error rate goes up higher and higher and higher. Okay, so when our threshold was at 50%, our sensitivity was 0.24. Okay, so I guess 1 minus that sensitivity, right, being this blue line, is at 0.756. But as at threshold of 0.2, our sensitivity is 0.586, so my error rate is only 0.414. And at threshold 0.1, my sensitivity is 0.751, so my error rate is lower. So I can keep kind of reducing my threshold, okay? But at some point, now I'm going to have a whole bunch of really high, I'm going to have too many false positives, okay? So if I reduce my threshold and I say, okay, anybody with over a 2% risk of defaulting gets rejected, now I have a really high false positive rate. Okay, so we don't want my false positive rates to get too high, but at the same time, I don't want to approve too many people who are going to default. And so this is a plot of kind of that relationship. We have 1 minus the sensitivity. We want to keep our sensitivity high and our this 1 minus sensitivity as low as possible. But we also want to have our 1 minus specificity kind of as low as possible, okay? This black line is the sum of our overall error rates in that overall how many default, like in total, like how incorrect are we? This, it's going to be the sum of these things, okay? So even though this line is like much higher, because there's only a few people who actually do default, this line, the black line, is only a tiny bit over our orange line here. Okay. We can also take a look at something known as the ROC curve, or our receiver operating characteristics curve, and this shows kind of all of the different possible error rates at different threshold levels. So the overall performance of a classifier can be measured by looking at the area under this ROC curve, okay, with the maximum possible value of 1, all right? And this is achieved if the curve starts at the lower left, goes straight up to the point, okay, FPR being our false positive rate and our true positive rate of 0 is our lower left, true positive rate of 1, and cuts all the way across the top right, okay? But, that's not really handy. A worthless classifier uses random guessing and it has an area AUC of under 0.5, okay? And we just draw a diagonal line. So what you want to see is a line that looks kind of like this, okay? You do want to see something like this, and the closer you can get to this top left corner is like the better performance, okay? And so here, a threshold of 0.5 corresponds to sensitivity of 0.243 and a false positive rate of 0.003. And that corresponds to this coordinate right here, okay? 0.243 and 0.003, okay? And as I increase my threshold at which I classify and reject somebody for a loan, okay, or a credit card, okay, at 0.2, my sensitivity is 0.583, so it's higher. My false positive rate is around 0.024, okay? And at threshold 0.1, this is where we are, okay? And as I increase my threshold, my false positive rate gets higher and higher and higher. Okay, and so you don't want this, but the overall kind of model performance, as far as like, because this is based off of this table of the predictions of yes and no and whether it got it correct or not. Okay, so it's what we want to have is something that operates perfectly based on kind of different thresholds. Obviously, we can't have perfect prediction, but as close as you can get to this top left corner is going to be the performance. So here it just says, I've just pointed out a couple locations on the ROC curve based on the true positive rate and the false positive rate. Okay. Real ROC curve is not going to have any of these locations labeled. You're just going to have this kind of blue curve here, and so we can ask R to draw the ROC curve for us. Okay, and so this is a kind of a tidy model thing, and this is what that ROC curve looks like. And I don't know if it gives us an area, but this is what that thing looks like. Okay. And and that's about it. There's you can kind of further expand this into I guess quadratic determinant analysis, not just linear determinant analysis, but quadratic determinant analysis. And so in that case, we allow for the variance to be different from classes. So linear determinant analysis, we presume that all of the different classes have the same amount of variance, and QDA, you have different amounts of variance. But you have more parameters to estimate, because now you have to estimate the mean and kind of your variance covariance matrix for each of your different classes. And so you need more data for an accurate model. Okay. As far as like where it fits on the different models on the spectrum of bias variance trade-off, LDA would be considered less flexible and have more bias but less variance, whereas QDA will be more flexible. Okay, more flexible. So that means less bias in the long run, but we'll have more variance depending on which data sets you have to train your model. And so if your data sets are good and reliable, then that's great. And if not, then you just have to kind of hope that your model is good. Okay, that's all I've got for you today. We'll finish about 10 minutes early, so we'll wrap things up here. And keep working with your groups on your different Kaggle projects, or on your Kaggle project. You can expect to see a classification Kaggle project get posted, and I'll explain a little bit more about that later this week. All right, we'll see you then.